Right now, at this very moment, a spacecraft roughly the size of a small car is moving through the darkness between the stars. Not heading toward another planet. Not circling a moon. Not in orbit around anything at all. Just moving outward, continuously, through a region so remote that the sun behind it has shrunk to a point of light, indistinguishable from thousands of other stars in the sky. That spacecraft is Voyager 1. It launched in September of 1977 before personal computers became widespread, before the internet existed, before most of the scientists currently working on the mission were born. It was designed for a 5-year mission to study Jupiter and Saturn. It completed that mission. Then it kept going, and going, and going. And as of right now, in 2026, it is still transmitting data back to Earth from a distance that strains comprehension, more than 15 billion miles away, sailing through interstellar space, the region between the stars, measuring the environment around it and sending the numbers home at a trickle of 160 bits per second. Not old data, not cached readings from a decade ago. Fresh data generated this week. Signals that left the spacecraft within the last day and arrived at a 70-meter radio dish in the Australian outback, where engineers decoded them and extracted measurements of what the interstellar medium looks like right where Voyager 1 is passing through it. Measurements of plasma density, magnetic field strength, the hum of charged gas in the space between stars. What Voyager 1 is detecting out there has surprised almost every scientist who has worked with its data. The picture assembling over the last decade since the spacecraft first crossed out of the solar system in 2012 is one of an interstellar medium that is structured, dynamic, turbulent, and full of the echoes of events that happened thousands and millions of years ago in the wider galaxy. It is not the featureless void that older models imagined. It is something far more interesting. The problem with talking about where Voyager 1 is that the human brain was not built for numbers like 15 billion. We evolved on a planet where the longest distances our ancestors regularly needed to think about were measured in miles or days of walking. Even when we stretch our sense of scale to continents or to the width of oceans, we are still in the thousands. 15 billion is so far beyond that range that the mind treats it like an abstraction, a number with a lot of zeros, filed in the same mental drawer as national debt figures or the age of the universe. So try it differently. Light, traveling at 186,000 miles per second, takes about 1.3 seconds to get from the Earth to the Moon. It reaches Mars in somewhere between 3 and 22 minutes, depending on where the two planets happen to be in their orbits. Jupiter, enormous. Distant Jupiter is about 43 minutes away at the speed of light. Saturn is about 1.5 hours. Uranus, roughly 2.7 hours. Neptune, the outermost planet, sits about 4 hours away from Earth at light speed. Voyager 1 is more than 22 hours away, more than 5 times farther than Neptune. And in November of 2026, when the probe crosses a threshold no human-made object has ever crossed before, that distance will reach 1 full light day, 24 hours at the speed of light, which works out to about 16.1 billion miles. The practical meaning of that number is severe. When engineers at NASA's Jet Propulsion Laboratory want to send a command to Voyager 1, they transmit it from a radio dish on the ground. That signal travels outward at the speed of light, the fastest anything can travel. And it takes a full day to arrive. Then the spacecraft processes the command and sends a response. That response takes another full day to travel back. 2 days minimum, just to have the most basic exchange of information. If I send a command saying good morning, Voyager 1, at 8 in the morning on Monday, the project manager Susie Dodd explained in a late 2025 interview, I'll get Voyager 1's response back on Wednesday morning at approximately 8. Not Tuesday, Wednesday. This is not a management inconvenience. It is a fundamental physical constraint imposed by the finite speed of light and the distances involved. There is no workaround. The signal travels as fast as anything can travel, and it still takes 2 days for a round trip. Every decision made about Voyager 1 has to account for that delay. Every command sent has to be correct, because there is no ability to correct it in real time. For most of the mission, the delay was measured in hours. Now it is measured in days, and the mission continues regardless. To truly appreciate what Voyager's data stream represents, it helps to understand the physics of deep space communication, not just the abstract numbers, but what those numbers mean in practice for the people trying to extract science from a signal that has traveled 15 billion miles. When Voyager 1 transmits, it uses a radio transmitter operating at about 22 watts, roughly the power of a refrigerator light bulb broadcasting at a frequency of roughly 8.4 gigahertz in the microwave range. That 22-watt signal radiates outward from the spacecraft's dish antenna, spreading across an ever-growing sphere of space. By the time it reaches Earth, after traveling more than 15 billion miles, the power arriving at any given square meter of the ground is so vanishingly small that writing it in watts would require a decimal point followed by dozens of zeros before you reached any significant digit. NASA's Deep Space Network exists specifically to receive signals this faint. The main dish in Canberra, Australia, Deep Space Station 43, is 70 meters across, roughly the width of a football field. Even with that enormous collecting area, engineers often need to combine it with other dishes in an array to extract a usable signal. The data comes in at 160 bits per second. For comparison, a single second of compressed audio music requires tens of thousands of bits. A photo from a modern phone camera contains millions of bits. Voyager's entire weekly science return is equivalent to a short text document that would take a fraction of a second to save on any device made in the last 30 years. At that rate, the value of the data has nothing to do with its volume. What matters is what the numbers represent. Direct readings of electron density in the local interstellar medium, at a specific location, at a specific time, made by the only instrument that has ever been there. Between May 2025 and February 2026, the situation became even more constrained. Deep Space Station 43, the only antenna in the world with enough transmit power to send commands to the Voyager probes, went offline for major upgrades. For most of those 9 months, no commands could be sent to either spacecraft at all. Both probes flew autonomously on stored instructions, collecting and transmitting data while the team on Earth could only listen. The antenna returned to service in early 2026, restoring the two-way link. The upgrades were designed to support future crewed lunar missions and the fact that maintaining contact with a 48-year-old probe 15 billion miles away, shaped those upgrade decisions is a testament to what Voyager is still contributing. To understand what Voyager 1 is encountering beyond the solar system, it is essential to understand what it left behind specifically. To understand what the solar system actually is at its largest scale. When most people picture the solar system, they picture the sun, the 8 planets, their moons, and maybe the Kuiper belt of icy objects beyond Neptune. That picture is accurate as far as it goes, but it misses the larger structure containing everything else. The sun does not just sit in space, passively illuminating the objects that orbit it. It breathes outward continuously, exhaling a stream of charged particles in all directions, electrons and protons and heavier ions, flowing at roughly 1 million miles per hour when they leave the sun's corona, traveling outward through the entire solar system and far beyond. This continuous outflow is the solar wind. As the solar wind expands outward, it carries part of the sun's magnetic field, twisted and stretched into a vast spiral structure, threading through all of the solar wind's volume. Everything inside the solar system is bathed in this flowing, magnetized plasma. Jupiter, Saturn, Uranus, Neptune, Earth, every moon, every asteroid, all of them live inside the solar wind. But the solar wind cannot expand forever. At some distance from the sun, it meets resistance to the pressure of the interstellar medium, the gas and magnetic fields and particle flows filling the rest of the galaxy. The interstellar medium pushes back, eventually at a distance somewhere around 80 to 100 astronomical units from the sun, 1 astronomical unit being the Earth-Sun distance. The solar wind runs out of momentum. It slows, piles up, and eventually stops. The boundary where it stops is the heliopause. The entire volume of space inside that boundary, the domain of the solar wind, is the heliosphere. The heliosphere is enormous. It extends in a rough sphere with a radius perhaps 4 times the distance from the sun to Neptune. From inside, you would never notice it. It has no atmosphere, no visible light, no edge you could see. It is a boundary in the behavior of particles and magnetic fields, a place where the sun's authority ends and something else begins. Crucially, the heliosphere also acts as a shield. It deflects and scatters a large fraction of the high-energy cosmic ray particles streaming through the galaxy. Without it, Earth's surface would be bathed in a much more intense radiation environment. Every human being alive today lives inside this invisible bubble, and most of us have never heard of it. Voyager 1 left that bubble in August of 2012. What it found on the other side has been the subject of intense scientific study ever since. Voyager 1 crossed the heliopause on August 25th, 2012. That date is now established beyond doubt, confirmed through careful analysis of plasma wave data and corroborated by independent measurements from multiple instruments over multiple years. At that moment, the spacecraft passed from the domain of the sun into the domain of the galaxy. The change in what the instruments detected was not subtle. The particles generated by processes within the heliosphere anomalous cosmic rays, energetic particles associated with the solar wind's interactions with the termination shock, dropped sharply and almost immediately. They did not slowly fade. They fell away as if a door had closed. On the other side of the boundary, those heliospheric particles were essentially absent. Simultaneously, the count of galactic cosmic rays particles originating from sources across the Milky Way, accelerated to enormous energies by supernovae and other violent events, jumped dramatically. These particles had been partially blocked and scattered by the heliosphere. Beyond the heliopause, there was nothing stopping them. They were simply there. In numbers the instruments had never recorded inside the solar system. The plasma density changed too. The outer heliosphere had a very sparse electron density, roughly 0.002 electrons per cubic centimeter. On the other side of the heliopause, that number jumped to roughly 0.08 electrons per cubic centimeter, about 40 times higher. This was one of the defining measurements confirming the crossing. And then there was the magnetic field and its peculiar behavior, which turned out to be one of the most scientifically debated findings of the entire mission. Before Voyager 1 crossed the heliopause, every measurement of galactic cosmic rays had been taken from inside the heliosphere. That means every measurement was filtered. The solar wind and the heliospheric magnetic field scatter and deflect cosmic rays, especially the lower energy ones. The more energy a particle has, the more easily it punches through the heliosphere's deflective fields. The less energy it has, the more strongly the heliosphere pushes back on it. Lower energy cosmic rays carry rich information about the recent history of stellar activity in the local galaxy, but they were significantly suppressed in every measurement ever taken from within the solar system. Nobody had ever seen the full, unfiltered population. Voyager 1 removed that filter. What it found was striking. The intensity of cosmic rays at energies below about 100 million electron volts per nucleon was roughly 15 times higher in interstellar space than at Earth's orbit. That number 15 is a direct quantitative measure of how much protection the heliosphere provides. If you remove the heliosphere entirely, the low-energy cosmic ray flux bathing Earth would jump by roughly that factor. The rate of cellular damage from cosmic ray bombardment would increase accordingly. Life on Earth's surface has been developing and persisting inside a radiation environment, shaped by the heliosphere's presence. That protection is not incidental, it is essential. Beyond the intensity, the energy spectrum of cosmic rays in interstellar space differed from predictions in ways that kept theorists occupied for years. Below about 50 million electron volts per nucleon, electrons are more abundant than protons, the opposite of what many standard models expected. This tells us something about how cosmic rays are generated and how they travel through the galaxy's magnetic field over long distances, but sorting out the full picture requires models more sophisticated than those available when Voyager made the crossing. The isotopic composition of cosmic rays has also yielded important information. By comparing the ratios of specific isotopes, forms of nitrogen and neon, for example measured by Voyager outside the heliopause with measurements made inside, scientists can calculate how much energy the heliospheric modulation process strips from particles on their inward journey. The calculations suggest that particles lose on average around 200 million electron volts per nucleon passing through the heliosphere. For low-energy cosmic rays, that energy loss is enough to render them essentially undetectable from Earth. They exist out there in substantial numbers, but arrive at inner solar system detectors, if at all, as shadows of their actual selves. Beyond counting particles and measuring their energies, Voyager 1 also detected something more subtle. whether cosmic rays arrive equally from all directions, or whether they show a preference. This property, called anisotropy, yielded some of the most intricate and unexpected findings of the mission's interstellar phase. In a broad sense, the galactic cosmic ray flux measured by Voyager is approximately isotropic. Particles arrive from essentially all directions, as you would expect from particles that have been bouncing around the galaxy for thousands of years, scattering off magnetic irregularities and losing all memory of where they started. But it is not perfectly uniform. Between late 2012 and 2017, Voyager's instruments recorded a series of events during which the cosmic ray count in one particular direction showed a measurable reduction, a shadow, while counts in other directions remained stable. The depletion was not random. It appeared at specific angles relative to the local magnetic field, and it came and went in ways that suggested a specific physical mechanism. Analysis pointed to the influence of transient disturbances from the sun. When a major solar eruption sends a pressure wave outward, that wave crosses the heliopause and compresses the local interstellar plasma and magnetic field. As it does, it creates a temporary region of enhanced, tightly coiled field, a magnetic barrier of sorts. Cosmic rays moving perpendicular to the local field find their paths bent and scattered by this barrier. The result is a temporary dip in the count of particles at a specific angle. The shadow of a solar disturbance, cast across the cosmic ray sky from more than 120 astronomical units away. This was not anticipated. It reveals that the sun continues to influence the cosmic ray environment in the interstellar medium beyond its own boundary. The heliosphere's edge is not a wall that cuts off all connection. It is a permeable membrane, and waves from the sun pass through it and continue to disturb the medium on the other side. The most continuously productive instrument Voyager 1 carries, one of only two still operating as of 2026, is the Plasma Wave Subsystem. Its name does not evoke romance, but its data has driven some of the most significant scientific papers to emerge from the mission in the last decade. The instrument consists of two antenna rods, extending roughly 10 meters behind the spacecraft. These antennas are sensitive to oscillations in the electric field around them specifically, the natural vibrations of electrons in the plasma through which Voyager is flying. Electrons in a plasma oscillate at a characteristic frequency determined by how densely packed they are. More electrons per cubic centimeter means a higher oscillation frequency, and by measuring that frequency, scientists can directly calculate the local electron density. Before Voyager crossed the heliopause, the most useful readings came from burst events, sharp spikes triggered when solar pressure waves compressed the local plasma and excited those oscillations. Each burst allowed a precise density measurement. Between bursts, there was nothing. The plasma was quiet. Scientists were effectively waiting for lightning to illuminate the landscape, then going blind again until the next flash. Then, gradually, something else emerged from the data. In 2017, a faint, narrowband signal appeared in the plasma wave records. Not a burst, not a spike, a continuous low-level tone sitting at almost exactly the plasma frequency. Persistent, steady, there day after day, week after week. It took careful analysis ruling out instrumental artifacts, cross-checking against noise models before the team was confident it was real. When a team led by Stella Koch-Ocker at Cornell University published their findings in Nature Astronomy in 2021, they described it as the first detection of a persistent plasma wave emission in interstellar space. The team used the phrase "the hum" in public communications, and the name stuck. James Corders of Cornell captured the distinction in a way that many found clarifying. A solar eruption reaching Voyager is like a lightning strike in a thunderstorm, bright, dramatic, brief. The persistent hum is like the steady patter of rain falling in the dark. Less spectacular, but always there, and more revealing precisely because of its constancy. What drives the hum is not definitively resolved. Two mechanisms are most likely: thermally excited plasma oscillations arising from the natural random motion of electrons due to their thermal energy, or quasi-thermal noise, a related process in which the random motions of individual particles generate wave-like disturbances in the surrounding field. Both would produce a signal at roughly the right frequency. Distinguishing between them requires either more detailed waveform analysis or a future spacecraft with more capable instruments. What matters is the consequence. Because the hum is continuous, Voyager 1 can measure the electron density of the interstellar medium around it on an ongoing, regular basis without waiting for solar events. Every week, the instrument logs another data point. Taken together, those points form the first continuous, in-place map of the very local interstellar medium, drawn one small measurement at a time. As the spacecraft travels deeper into territory no probe has ever crossed. The density map that the persistent hum has enabled tells a story about the environment through which Voyager 1 is moving. When Voyager crossed the heliopause in 2012, the electron density jumped from about 0.002 electrons per cubic centimeter inside the heliosphere to roughly 0.08 outside. Then the hum, detected from 2017 onward, began filling in the gaps between solar-driven measurement events, showing how the density evolved not just at moments of excitation, but continuously across the quiet stretches between those events. What the map shows is that the density did not stay flat after the initial jump. It kept rising. By 2015, it had reached roughly 40 times the outer heliosphere baseline. This continued increase reflected the density gradient of the very local interstellar medium, denser closer to the heliopause, somewhat less so farther out. As Voyager moved away from the boundary, the density kept climbing for several years. Then, around 2019 to 2020, the gradient flattened out. The density stabilized in a range around 0.12 to 0.14 electrons per cubic centimeter. This plateau suggests Voyager had moved out of the steep transition zone immediately outside the heliopause and into a broader, more uniform region of the medium with its own characteristic density. The roughly 7-month data gap caused by the 2023 to 2024 communications crisis is unrecoverable. Those measurements are simply gone. But the values on either side of the gap are consistent enough that scientists are reasonably confident no major discontinuity occurred during those months. As of the post-recovery data, the electron density around Voyager 1 sits at approximately 0.14 electrons per cubic centimeter, slightly lower than the peak observed in late 2023, but within the stable range that has characterized the region for the past several years. This density is notably higher than some early models predicted for the local interstellar medium in this part of the galaxy. Whether it represents typical conditions for the Sun's immediate cosmic neighborhood or a localized feature of the region, Voyager is currently traversing is something only additional data or a future probe traveling in a different direction can resolve. The other active instrument on Voyager 1 as of 2026 is the magnetometer. It measures the strength and direction of the magnetic field at the spacecraft's location, and its readings have generated sustained scientific debate in the most productive sense, the kind that drives new theory, revised models, and eventually deeper understanding. Here is what was expected when Voyager 1 crossed the heliopause. Inside the heliosphere, the magnetic field has a well-defined orientation, the Parker spiral, spiraling outward as the solar wind carries it away, and the sun's rotation winds it up. In the outermost heliosphere, that spiral has mostly unwound, and field lines run roughly radially. The interstellar magnetic field, shaped by the broader structure of the galaxy and the local interstellar cloud, was expected to point in a substantially different direction, offset by many degrees from the heliospheric orientation. When Voyager 1 crossed the heliopause, the magnetic field barely changed direction at all. The plasma density jumped. The particle populations changed dramatically, but the magnetic field direction remained almost the same as inside the heliosphere. Nature hasn't read the theorist's papers, one researcher observed. The explanation that eventually emerged required a more detailed picture of what the heliopause does to the surrounding field geometry. As the solar system moves through the local interstellar cloud at roughly 55,000 miles per hour, it drags against the surrounding medium. The interstellar magnetic field lines draping over and around the heliosphere get wrapped and deflected as the system moves like fabric stretching around a ball. Near the heliopause, those field lines are bent to run more nearly parallel to the heliospheric field, creating a transition zone where the magnetic environment is still partially shaped by the heliosphere's presence, even though the plasma properties have already changed to interstellar values. A 2015 study predicted Voyager would not emerge from this magnetically disturbed region until it reached roughly 150 astronomical units from the Sun. Voyager is now beyond 170 astronomical units and moving outward at roughly 3.6 astronomical units per year. So it is approaching or may already be in the region of undistorted interstellar field. Whether the magnetometer will still be operating to confirm the transition is one of the many questions hanging over the mission's remaining years. The magnetometer has also been tracking the anomalous field elevation that began around 2020. The magnetic field strength measured around Voyager 1 rose that year and has remained elevated. Whether this reflects an extraordinarily long-lived solar pressure wave, a genuine density feature of the nearby interstellar medium, or the probe moving into a region of locally enhanced field is not yet resolved. It is one of the open questions that makes Voyager 1's continued operation scientifically essential. Among all the things the Voyager probes detected at the heliopause, the finding that has captured the most public attention is the discovery of an intensely hot boundary zone right at the edge of the solar system. Both Voyager spacecraft, as they crossed the heliopause, measured temperatures in the surrounding plasma of between 30,000 and 50,000 Kelvin. For comparison, the surface of the Sun sits at roughly 5,500 Kelvin. The boundary zone is 5 to 10 times hotter. These numbers sound impossible until you understand what temperature means in very thin plasma and how it differs from everyday heat. Temperature is a measure of how fast particles are moving. In thick air, fast-moving particles constantly collide with everything around them, including you, and you feel that energy transfer as warmth. In the plasma at the heliopause, the temperature is enormous, meaning individual electrons and ions are moving at extraordinary speeds. But the density is extraordinarily low. There are almost no particles per cubic centimeter. The energy transferred in any individual collision is negligible, and collisions are rare. If you could somehow place an unprotected hand into the heliopause plasma, you would not feel heat. You would lose heat to the near vacuum around you and freeze, not burn. The temperature is real. It tells us the particles are moving very fast. But it does not mean the heliopause is hot in any intuitive, everyday sense of the word. Why the particles are moving that fast, right at that boundary, is the interesting question. The leading explanation involves magnetic reconnection. At the heliopause, the magnetic field lines for the heliosphere and those from the interstellar medium press against each other. When field lines with certain orientations meet under sufficient pressure, they can snap apart and rejoin in new configurations, releasing stored magnetic energy as a burst of particle acceleration. The result is intense. Local heating right at the boundary. Both Voyager probes detected this hot zone as they crossed, confirming it as a consistent feature of the heliopause boundary rather than a local accident. Voyager 2's crossing in November 2018, with its plasma instrument still functioning, gave the first real-time direct confirmation. The wall of heat is real, it is reproducible, and it likely exists all the way around the heliopause boundary, wherever the two magnetic domains press against each other. The discovery has implications beyond theoretical physics. Any future interstellar probe would cross this boundary. Any spacecraft crossing from the heliosphere into interstellar space would pass through this thermal zone. Understanding it matters for designing instruments robust enough to survive the transition and for predicting how the boundary environment affects sensitive measurements. One of the most counterintuitive revelations from Voyager 1's years in interstellar space is that the Sun's influence does not end at the heliopause. It continues to reach outward, past its own boundary, into the medium it nominally does not control. The mechanism is pressure waves. When a large coronal mass ejection erupts from the Sun, it fires a massive release of magnetized plasma outward at millions of miles per hour. This sends a wave of pressure through the solar wind, which travels outward, slamming through the termination shock and heliosheath, gradually losing energy as it goes. Eventually it reaches the heliopause. It does not stop there. The wave is transmitted into the interstellar medium, continuing outward as a compression front in the interstellar plasma. When that front reaches Voyager 1, the instruments register it clearly. The electron density temporarily rises as the plasma is squeezed together, and the plasma wave instrument registers a jump in oscillation frequency. The magnetometer shows a corresponding increase in field strength. Then, as the wave passes, both readings return toward baseline. Clear events of this kind were observed in 2012 and 2013, shortly after the heliopause crossing. Scientists could work backward, matching the events to known solar eruptions and calculating travel times across the more than 120 astronomical units between the Sun and Voyager. The correlation was excellent. More recent events have been less clean. The anomalous magnetic field elevation that began in 2020 initially looked like a solar-driven event. But unlike earlier events, which lasted months and faded, this one persisted. Months became years. Some researchers began questioning whether it was solar-driven at all, or whether Voyager had simply moved into a region of the interstellar medium that was inherently denser and more magnetically intense. Others suggested an unusually prolonged solar activity episode. Still others proposed that Voyager was entering a transition zone at the outer edge of the local interstellar cloud. As of the most recent available analysis, the question remains open, but the larger point stands regardless. The Sun punches through its own boundary with regularity, disturbing the interstellar medium for unknown distances beyond the heliopause. The boundary is not a wall. It is a permeable membrane through which the Sun's dynamic behavior continues to echo outward into the galaxy. Nothing in the story of Voyager 1's interstellar journey has been more technically dramatic than what happened between November 2023 and June 2024. On November 14, 2023, Voyager 1 stopped making sense. The signal was still arriving, engineers could confirm the spacecraft was alive, still transmitting, still receiving commands. But what the signal contained was gibberish. Instead of the structured binary data stream that had been arriving reliably for decades, Voyager was sending what looked like a repeating pattern of alternating ones and zeros, a monotone dial tone that carried no usable information. No engineering data, no science data, nothing. For 5 months, the team worked in near darkness. Commands were still transmitted, in the hope they were being received and acted on. Engineers spent hours examining the garbled output, looking for any structure that could be interpreted. It would be the biggest miracle if we get it back, project manager Suzanne Dodd said in early 2024. We certainly haven't given up. The problem was eventually traced to the flight data subsystem, one of Voyager's 3 onboard computers. The one responsible for collecting data from all the science and engineering instruments, packaging it into a coherent stream, and handing it off to the radio for transmission. The FDS has a total memory of about 69 kilobytes. That is less memory than many word processing documents. This machine, running on 1970s hardware with a processor speed measured in the hundreds of kilohertz, has been performing its job continuously for nearly 50 years. In March 2024, engineers sent a special command that prompted the FDS to dump the entirety of its own memory and transmit it home. That dump arrived after a 22-hour delay. An engineer at JPL spent hours carefully decoding the raw readout, mapping each section of memory against the functions it was supposed to serve. The diagnosis was specific. A single chip responsible for storing a portion of the FDS software had failed. About 3% of the FDS memory was corrupted lightly, from a cosmic ray strike or simple wear after 46 years of continuous operation. The chip could not be repaired. It was 15 billion miles away, and even if it were reachable, physical hardware repair in deep space is not possible. The team had to work around it. What they devised was a form of distributed digital surgery performed across the solar system. The software that had been stored in the failed chip was split into sections small enough to fit in the scattered empty spaces elsewhere in the FDS memory. Each section was revised so that together they could still function as a coherent whole. Every pointer in the rest of the system, every instruction that told the computer where to find different pieces of code, was updated to reflect the new locations. Some additional memory space was freed by identifying and removing routines that would never be needed again. Code written for faster data transmission rates used decades ago when Voyager was close to Earth. Code that had been riding along through interstellar space, doing nothing. The rearranged software was uploaded on April 18th, 2024. The signal took 22.5 hours to arrive. The team waited 45 hours for the round trip to complete. On April 20th, the response came back coherent. Voyager was talking again. Through May and June 2024, each of the 4 remaining science instruments was brought back online individually, each requiring its own patch and verification. By mid-June, all 4 were returning usable science data. The mission was fully restored. Recovery from the 2023 to 2024 crisis did not mean the engineering challenges were over. In some ways, it bought time for a deeper, slower crisis that has been building since launch: the inexorable loss of electrical power. Voyager 1's power comes from 3 radioisotope thermoelectric generators. These devices convert the heat produced by decaying plutonium-238 directly into electricity with no moving parts. At launch in 1977, they produced roughly 470 watts. Every year since, the output has declined by approximately 4 watts as the plutonium slowly transforms through radioactive decay. By the mid-2020s, available power had fallen below 200 watts. The transmitter alone requires roughly 20 watts. The computers, heaters, attitude control systems, and the remaining instruments take the rest. The margin is desperately thin. Managing this decline requires constant, painful decisions. Turn off a heater to save power, and you risk allowing a fuel line to freeze in the extreme cold of interstellar space temperatures approaching absolute zero in the absence of a heat source. If a fuel line freezes, the thrusters cannot fire. Without thrusters, Voyager cannot keep its antenna aimed at Earth. If the antenna drifts off target, the signal is lost and the mission ends. The calculation is unforgiving. Every instrument that stays on draws power, and every watt of power not consumed by instruments potentially extends the spacecraft's life. The team made the decision long ago, before many current engineers joined the project, to plan the sequence of instrument shutdowns in advance, so each one could be made thoughtfully rather than in crisis. That plan had 7 of the original 10 instruments shut off by the mid-2020s. The cameras went dark in 1990, freeing up significant resources. Various others followed over the years. In February 2025, the cosmic ray subsystem was powered down the same instrument that detected the dramatic surge of galactic cosmic rays when Voyager first crossed the heliopause, that had been building a decade's worth of data in the local interstellar medium. It was shut down not because it failed, but because the power arithmetic could no longer justify keeping it running. Then, in April 2026, the Low Energy Charged Particles instrument, the LECP, was powered down as well. It had operated almost without interruption since 1977, nearly 49 years. The decision came partly because a routine spacecraft maneuver in February 2026 caused a power draw that nearly triggered the automatic fault protection system, which would have put Voyager into emergency safe mode without warning. The LECP was next on the planned shutdown list, and its power went off on April 17th, 2026. Commands took 23 hours to arrive. The shutdown sequence took about 3 hours and 15 minutes to complete. As of that shutdown, Voyager 1 has 2 science instruments still operating: the plasma wave subsystem and the magnetometer. Both are currently described by mission managers as working well, but they are running on borrowed time, with power margins razor thin and the next planned shutdown potentially arriving as early as 2027. The engineering team has been developing a more creative approach to buy additional operational life. The plan is called the Big Bang. The idea involves switching 3 heating systems that currently keep Voyager's thruster fuel lines above their freezing point over to 3 alternative devices that accomplish the same function while using a total of nearly 10 watts less power. 10 watts, in the context of a spacecraft losing 4 watts per year, represents the equivalent of 2.5 years of the annual RTG decline reversed. If it works, it could delay the next instrument shutdown by at least a year, possibly more. It might even create enough headroom to restart one of the recently shut down instruments for periodic use, rotating between different instruments to gather different types of data over time rather than running any single one continuously. The plan will be tested on Voyager 2 first, in the summer of 2026. Voyager 2 has slightly more power margin and is somewhat closer to Earth, making it a more forgiving testbed. If the maneuver works there, it will be attempted on Voyager 1 sometime after. The risk is genuine. Any of the 3 alternative warming devices could fail during the switchover, leaving a fuel line exposed to the cold of interstellar space. If the fuel line freezes, the thrusters become inoperable. Without thrusters, the antenna drifts away from Earth. The mission ends. That is a real failure mode, not hypothetical. The team has to weigh it against the certainty of running out of power without the maneuver. The track record offers some reassurance. In 2017, engineers successfully restarted a set of backup thrusters on Voyager 1 that had not been fired in 37 years. The fuel valves opened, the combustion chambers fired, the spacecraft responded correctly. If systems dormant for nearly 4 decades could be revived, a power routing change has a reasonable chance of success. Under current projections, if the Big Bang works on both probes, the operational mission could extend into the early 2030s. Voyager 1's measurements have also enabled a test of what the heliosphere actually looks like when seen from the outside, and the answer has proven more complicated than decades of theory predicted. For many years, the standard picture had the heliosphere shaped like a comet. The solar system moves through the galaxy at roughly 55,000 miles per hour. The interstellar medium flows past the heliosphere from one side, and this flow was expected to push the heliosphere into an asymmetric shape, blunt on the side, facing into the galactic wind, elongated into a long tail on the opposite side, much like a comet streaming away from the sun. When the two crossing distances were compared 121 astronomical units for Voyager 1 crossing in the northern direction, 119 astronomical units for Voyager 2 crossing in the south, they were remarkably close, less than 2% different. If the heliosphere had a dramatically elongated tail, crossings in different directions should have yielded very different distances. The near equal numbers suggest the heliosphere may be more spherical than the comet model predicted, at least in the directions the two probes sampled. The IBEX satellite further complicated the comet model. In 2009, IBEX discovered a bright ribbon of unusually intense emission running around the sky at heliopause. Distance is a feature that the comet-shaped heliosphere models had not anticipated and cannot cleanly explain. Something unusual is happening along that ribbon. Either the interstellar magnetic field interacts with the heliosphere boundary in a way that concentrates particles there, or the ribbon reflects a region where the interstellar field is oriented in a specific way relative to the line of sight. Neither explanation fully satisfies the data, and the ribbon remains one of the outstanding puzzles in heliophysics. The IMAP mission, launched in 2024 to improve on IBEX's observations, will provide better resolution maps of the heliosphere boundary over the coming years. But no remote sensing can substitute for direct measurement from inside the interstellar medium. The combination of Voyager's in-place data with IMAP's boundary maps should, over the next several years, produce a substantially clearer picture of the heliosphere's true shape. One that will constrain the cosmic ray environment of the inner solar system and inform plans for any future mission that needs to cross the heliopause. The solar system is not in a random spot in the Milky Way, and the specific neighborhood it inhabits directly shapes the environment Voyager 1 is measuring. The Sun sits about 26,000 light-years from the galactic center, in a region of the disk between two major spiral arms. At this location, the Sun is inside a large, low-density cavity called the local bubble, a region carved out by a series of supernova explosions over the last few million years. Those explosions heated the surrounding gas to extremely high temperatures and drove it outward, creating an irregularly shaped void roughly 1,000 light-years across, filled with very hot, very tenuous plasma at temperatures around 1,000,000 Kelvin. Inside the local bubble, near its inner edge, sits the local interstellar cloud, sometimes called the local fluff. This is a region of gas and plasma that is somewhat warmer and denser than the average material inside the local bubble. Temperatures around 6,000 to 8,000 Kelvin, partially ionized, with a density higher than the near vacuum of the surrounding hot plasma, but lower than typical neutral interstellar material. The Sun has been traveling through the local fluff for somewhere between 44,000 and 150,000 years, depending on the model, and current estimates suggest it will exit the cloud sometime between now and about 4,000 years from now. The density of the local fluff determines how large the heliosphere is. The heliosphere's extent is set by the balance between the outward pressure of the solar wind and the inward pressure of the surrounding medium. If the surrounding medium gets denser, the heliosphere shrinks. If the sun were to exit the local fluff and enter the very low-density hot plasma of the local bubble interior, the heliosphere might expand dramatically, potentially large enough to encompass a significant portion of the Oort cloud. The cosmic ray environment at Earth would change, with fewer low-energy particles being blocked by the compressed boundary. If instead the sun entered a region denser than the local fluff, the heliosphere might be compressed far enough inward to change the radiation environment of the outer solar system. Voyager 1's measurements of electron density and magnetic field in the interstellar medium just outside the heliosphere are direct observational constraints on the current state of the local fluff. Every data point from the remaining instruments is, in a broader context, a measurement of the environment that determines how large the sun's protective bubble is and has been for the entire history of life on Earth. One thing the Voyager data has made unmistakably clear, and that the simple phrase empty space completely fails to convey, is that the material between the stars is not empty, not simple, and not quiet. The interstellar medium is a mixture of components in different physical states. The most abundant by number of atoms is neutral hydrogen individual hydrogen atoms drifting through space, emitting radio waves at a specific frequency when the electron in the atom flips its spin. Mapping this emission across the sky has been one of the primary methods for mapping the structure of the Milky Way. Beyond neutral hydrogen, there are heavier atoms: carbon, oxygen, nitrogen, silicon, iron, and many others, mostly the processed remnants of earlier generations of stars that exploded as supernovae and scattered their nuclei into space. There are molecules found in the densest and coldest clouds where stars are forming, including molecular hydrogen, water, carbon monoxide, and dozens of organic compounds of varying complexity. There is dust, tiny solid grains between roughly 1/10 of a micron and a few microns in size, made of silicates and carbon compounds, sometimes coated in ices of water, methane, or ammonia. Dust grains absorb ultraviolet light, shield the interior of dense clouds, and serve as surfaces where complex chemistry can occur. And there is the ionized component plasma, electrons and ions liberated from their parent atoms by ultraviolet radiation from hot stars or by the shock heating of supernova remnants. This is the component that Voyager 1's plasma wave subsystem directly measures. The electron density that the persistent hum allows the team to track continuously is a measure of how much of the surrounding gas has been ionized, how many of the atoms have lost an electron and become charged particles drifting in the ambient magnetic field. In the very local interstellar cloud that the sun is currently inside, the gas is roughly 1/4 to 1/3 ionized, partly neutral, partly ionized, in proportions set by the balance between ionizing radiation from nearby hot stars and the rate at which ions and electrons recombine. Voyager 1 is measuring this mixture directly, in place, at a specific location along a specific trajectory. That measurement cannot be made by any telescope or satellite inside the solar system. It requires being there. In November of 2026, specifically around November 13th to 15th, if current estimates hold, Voyager 1 will cross a boundary no human-made object has ever reached. The distance from Earth to the spacecraft will equal 1 light day. The distance light travels in 24 hours. That works out to roughly 16.1 billion miles, or 25.9 billion kilometers. This is a number worth sitting with because it is not just a round figure to acknowledge and move past. It represents a genuine threshold in what communication with a distant machine looks like. For Apollo, the communication delay was measured in seconds. For Mars missions, minutes. For Voyager, during most of its planetary-era journey, hours, now days. When Susie Dodd sends a good morning message to Voyager 1 at 8 o'clock on a Monday morning, she will receive a response on Wednesday morning at approximately 8. 2 full days for a single exchange, traveling at the maximum possible speed. The 1 light day milestone also puts the larger journey in perspective. Voyager 1 moves at roughly 38,000 miles per hour, fast enough to cross the continental United States in under 3 minutes. In nearly 50 years of continuous flight at that speed, it has covered about 0.003% of the distance to the nearest star. Not 3%, not 1%, 0.003%. The nearest star is so far away that Voyager would need roughly 73,000 years to reach it at its current speed. The galaxy is not a place humanity can cross with the technologies we currently have or can plausibly imagine building. What this means is that Voyager 1 is not heading anywhere in any meaningful human sense. It is not going to arrive somewhere. It will keep flying through the interstellar medium into the inner edge of the Oort cloud in about 300 years. Through the Oort cloud over the following tens of thousands of years, and then into open interstellar space, carrying a piece of Earth through the dark between the stars for billions of years after the last signal fades. Voyager 2 is not expected to reach 1 light day distance until around 2035. And even the most optimistic projections do not expect it to still be operating at that point. So the 1 light day milestone belongs to Voyager 1 alone, a private record that no instrument will witness, happening quietly in the interstellar medium while the data trickles home at 160 bits per second. On the side of Voyager 1, bolted to its exterior, is a 12-inch gold-plated copper disc. It was placed there with care and intention in the summer of 1977, when the mission's scientific goals were the driving priority, but there was still room for something more, a message to whoever or whatever might someday find the spacecraft. The record contains 115 images encoded in analog form. Pictures of Earth from space, of humans from many cultures, of animals and plants, of mathematics and physics, of the structure of DNA. It contains greetings spoken in 55 languages, from Akkadian not spoken in 4,000 years to modern Chinese. It contains sounds: rain, wind, surf, thunder, a mother and child, the calls of whales and birds and crickets. And it contains 90 minutes of music, selected from across human cultures. Bach, Beethoven, Chuck Berry's Johnny B. Good, Indian classical music, music from Azerbaijan, Peru, Senegal, Bulgaria, and the Solomon Islands. One detail about the record's creation that rarely gets mentioned. Among the data encoded on it are brainwave recordings made by Andrian, who served as one of the project's creative directors and was, at the time of the recording, newly engaged to Carl Sagan. she asked to be recorded while thinking specifically about the history of Earth, the emergence of life, the development of civilization, the experience of love, the questions she most wanted to convey about what it means to be human. Those electrical patterns from her brain are on the record. Somewhere in interstellar space, moving at 38,000 miles per hour, are the encoded thoughts of a person who was in love. The cover of the record includes a diagram explaining how to play at the rotation speed and stylus geometry. It includes a map of pulsars that allows any finder to triangulate the location of the solar system in the galaxy, using the precisely known rotation frequencies of specific neutron stars as references. It includes a depiction of a hydrogen atom undergoing a spin flip transition, a universal reference for length and time based on the most abundant element in the universe. The record was designed to survive 1 billion years in the vacuum of space. Whether anyone will ever find it, or find it and understand it, is unknowable. What is certain is that it is there, flying through interstellar space, carried by a machine built by human hands in the 1970s, moving silently away from home at a speed that seems fast until you hold it against the distances involved, carrying a portrait of what Earth was and what the people on it hoped they were. The people keeping Voyager 1 alive in 2026 face a set of constraints that has no real parallel in the history of engineering. They are maintaining a machine older than most of them, built from hardware no longer manufactured, programmed in a language few developers today have used, flying at a distance where any mistake takes 2 days to even partially correct. The software running on Voyager's flight data subsystem was originally written in Fortran 5, version of Fortran from the mid-1970s. Some of it was later ported to Fortran 77, and some routines were rewritten in C as the team modernized their approach over the decades. But large sections of the code have never been touched since the early 1970s. They are the original instructions, tested on the ground by engineers who are now in their 70s or 80s, or no longer living. To understand what a particular piece of Voyager software is doing, the current team sometimes has to find documentation that exists only on paper, or reach out to engineers who were present at the original design to ask what a specific instruction was meant to accomplish. The 2024 repair made this challenge viscerally clear. When the team mapped out the FDS memory to find spaces where the relocated code fragments could fit, one of the things they did was identify routines that were no longer needed software written for situations that would never occur again. Voyager was programmed with multiple data transmission rates for use when it was close enough to Earth to communicate faster. Those faster rates would never be used again. The routines occupying their memory space were identified, understood, removed, and that space was repurposed. Doing that, safely removing code from a 48-year-old spacecraft's computer without accidentally breaking something else, required the kind of deep institutional knowledge that only comes from decades of careful documentation and the accumulated expertise of a small, dedicated team. The communication latency adds another layer of difficulty to everything they do. When an engineer writes a command to send to Voyager, there is no way to test it first on an identical system. There is no identical system. The spacecraft is the original, affected by 48 years of radiation exposure, thermal cycling, and the accumulated effects of operating in one of the most extreme environments imaginable. The team can model what a command should do. They can review it thoroughly. But they will not know what it actually did until the response arrives, 22 hours after the command was sent. Every action requires a certainty and deliberateness that has become unusual in an engineering culture accustomed to instant feedback and rapid iteration. Taken together, the data coming from Voyager 1 tells a story that is different in important ways from what scientists expected before the mission crossed into interstellar space. The expected picture had the solar system sitting inside a protective bubble with a relatively clean boundary. Outside, the bubble was interstellar space, thin, quiet, mostly uniform, with a distinct magnetic field pointing in a different direction from the one inside the heliosphere. The transition from inside to outside was expected to be relatively sharp and well-defined. Beyond it, things would be simpler and more stable. The actual picture is more complicated in almost every respect. The heliopause boundary is thermally active, a frontier where magnetic reconnection produces temperatures thousands of times higher than anyone expected. The magnetic field on both sides of the boundary is unexpectedly similar in orientation, pointing to a disturbed transition zone, extending for tens of astronomical units beyond the nominal boundary. The interstellar medium in Voyager's neighborhood is not uniform but structured, showing gradients, turbulence, and features that vary with position. The sun reaches past its own boundary, sending pressure waves into the interstellar medium that disturb particle populations and magnetic fields for unknown distances. The background radiation environment is 15 times more intense than what reaches Earth, quantifying for the first time how much protection the heliosphere provides. And the medium itself hums continuously, faintly, carrying information about its density in every moment. Each of these findings has changed how scientists model the local interstellar medium, the structure of the heliosphere, and the conditions that have prevailed around Earth throughout its history. Each has generated a body of follow-on theoretical work. And each was discovered not by a telescope, not by remote sensing, not by inference from distant observations, but by an instrument that was actually there, measuring what it found. Voyager 1 is the only direct source of in-place measurements from interstellar space. When it goes silent, that will remain true for an unknown but substantial number of years. No replacement mission is funded or approved. The interstellar probe concept, a dedicated mission with modern instruments designed to cross the heliopause in 15 to 20 years, has been studied, praised, prioritized by the scientific community, and not funded. The two remaining active instruments on Voyager 1 may represent the only real-time window into the local interstellar medium for the rest of this century. Sometime in the late 2020s or early 2030s, Voyager 1 will fall silent. There is no dramatic ending planned, no ceremony, no final command. The power will drop below the threshold the transmitter needs, or a heater will fail and a fuel line will freeze, or some critical system will reach the end of what 48 years of operation in interstellar space has left it able to do. Something will give, the trickle of data will stop, the probe will continue flying. There is nothing in interstellar space to slow it down, no air resistance, No gravitational well close enough to pull it in. In about 300 years, it will reach the inner edge of the Oort cloud. In 10 to 30,000 years, it will emerge from the far side of the Oort cloud, fully beyond the sun's gravitational domain. Around the year 40,272, it will pass closest to a faint red dwarf called Gliese, 445 coming within 1.6 light years of it, close in astronomical terms, before continuing outward through the galaxy. Long after everyone alive today is gone, long after every institution and civilization we know has transformed beyond recognition, Voyager 1 will be somewhere in the Milky Way, still moving, still carrying its golden record, still carrying the encoded brainwaves of a woman who was thinking about love on a summer day in 1977. Still carrying the mathematical diagrams and the music and the sounds of rain falling on Earth and the greetings in 55 languages. What the data still coming from it tells us right now is that the space between stars is not empty. It hums, it breathes, it carries the echoes of ancient stellar explosions. It has structure and turbulence and an active magnetic field. The heliosphere we live inside is not a passive feature of our astronomy. It's an active, living boundary shaped by the ongoing interaction between a star and a galaxy that is far more dynamic than it appears from the quiet interior of a stable solar system. Voyager 1 is on the other side of that boundary, and it is still talking. Still sending home a trickle of numbers that tell us what the galaxy looks like from the inside. Still doing, with a refrigerator light bulb's worth of power and 68 kilobytes of memory, science that no other object in human history has ever done. There is a small team at NASA's Jet Propulsion Laboratory in Pasadena, California, whose job is to maintain contact with the spacecraft that has been flying since before most of them were born. They work with documentation printed on paper because the digital systems of the 1970s did not produce files that modern computers can easily open. They write software in a programming language Fortran that fewer and fewer universities still teach. They send commands that take nearly a full day to arrive, and they receive responses that take another day to come back. And they must make decisions in between those 2 points based on their best understanding of what a 48-year-old machine in interstellar space is capable of doing. This team is not large. It has shrunk over the decades as budgets have tightened, and as the mission has moved into a phase where there are fewer dramatic events and fewer obvious scientific milestones to point to when justifying continued funding. The people who have remained have done so out of a particular kind of commitment, not just to a mission, but to the idea that the data coming from 15 billion miles away is worth the effort of receiving it properly. What that effort involves on a day-to-day basis is more mundane than dramatic. Engineers monitor the signal quality from the deep space network. They track the power levels reported in Voyager's engineering data, watching for any unexpected drops that might signal a problem. They analyze the science data from the 2 remaining instruments, checking for calibration drift, comparing new readings against historical baselines, flagging anything that looks anomalous. They plan ahead every instrument shutdown, every thruster firing, every software adjustment, with the knowledge that any mistake costs days or weeks before it can be identified and corrected. The generational challenge is real. The engineers who designed Voyager understood its internals in a way that can only be fully matched by building something yourself. That knowledge does not transfer completely through documentation. When a component behaves unexpectedly, the people with the deepest intuition about why are often the ones who designed it, and those people are mostly gone. What remains is a combination of careful documentation, institutional memory held by the most experienced current team members, and an approach to anomaly resolution that is methodical and conservative rather than fast and improvised. The 2024 repair was, in some ways, the ultimate test of this approach. The team spent months working through the problem in a way that was thorough rather than hasty. Even though the stakes, the potential permanent loss of the mission, were severe. They gathered all available data before proposing a solution. They worked through the implications of every proposed change before implementing any of them. And they got it right. Not because they were lucky, but because decades of careful practice had made them very good at a job that has no parallel anywhere else in human engineering. A point that tends to get lost in discussions of modern astronomy is how much of what we know about the universe comes from observations made at enormous distance through telescopes that collect light from objects millions or billions of light years away. Modern astronomy is an extraordinarily powerful tool for understanding the large-scale structure of the universe, the distribution of galaxies, the properties of black holes, the cosmic web of filaments and voids. But there are things that cannot be learned from distance, no matter how powerful the telescope. The interstellar medium is one of those things. You can observe it from outside, measure the absorption of light from distant stars as it passes through the medium, detect its radio emissions, map the magnetic field through the polarization of light it imprints. All of these indirect methods have been used for decades and have produced real knowledge. But they cannot tell you what the electron density is at a specific location. They cannot measure the magnetic field strength and direction at a specific point in the medium. They cannot detect the local turbulence in the plasma or the passage of a pressure wave from a solar eruption. All of those things require an instrument that is physically present at the location. Voyager 1 is that instrument. It is the only such instrument in the history of humanity. This is why the scientific community's endorsement of a future interstellar probe mission has been so consistent and so strong. The measurements that Voyager 1 is making cannot be replicated by any telescope, any satellite in Earth orbit, or any spacecraft inside the heliosphere. They require being there. And as long as Voyager 1 is the only object ever to have been there, its data is the only data of its kind. The IBEX and IMAP satellites can map the heliosphere boundary remotely by detecting high-energy neutral atoms that travel inward from that boundary. That mapping is valuable. It produces images of the heliosphere's outer structure that Voyager alone cannot provide. But the images are indirect. They show the heliosphere as a distant object, the way a photograph shows a place you have never visited. Voyager's data shows the interstellar medium from the inside. The way a person's account of being in a place is different from any photograph. The combination of those two approaches, remote mapping plus in-place measurement, is what the scientific community most wants for the next era of heliospheric research. The remote mapping is being done. The in-place measurement depends entirely on two instruments on a spacecraft that is approaching the end of its operational life and has no approved replacement. Step back far enough from the specific measurements and the engineering crises, and a larger picture emerges from what Voyager 1 has found since 2012. A picture of the sun's place in the galaxy that is more interesting and more dynamic than what was understood before. The heliosphere, it turns out, is not a fixed structure. It breathes. As solar activity rises and falls over the 11-year solar cycle, the output of the solar wind changes, and the size and shape of the heliosphere fluctuate in response. When solar activity is high and the solar wind is stronger, the heliosphere expands slightly. When activity is low, it contracts. Both Voyager probes crossed the heliopause at slightly different distances, partly because the solar cycle was in a different phase when each made the crossing. The heliosphere that Voyager 1 passed through in 2012 was not exactly the same heliosphere that Voyager 2 passed through in 2018. This breathing is significant because it means the cosmic ray environment inside the solar system varies with the solar cycle. At solar minimum, when the heliosphere is slightly smaller and the solar wind is weaker, more galactic cosmic rays penetrate inward. At solar maximum, somewhat fewer get through. This variation has been measured for decades from Earth and from planetary missions. Voyager 1 can now constrain the models of how much cosmic ray flux gets modified across the full extent of the heliosphere, from the inner solar system all the way out to the heliopause. Beyond the solar cycle, the heliosphere responds to the sun's movement through the galaxy on much longer timescales. As the sun passes through regions of different density in the interstellar medium, different types of clouds, different distances from the nearest hot stars producing ionizing radiation, the pressure balance that determines the heliosphere's size changes. Over millions of years, the heliosphere may have been significantly larger or smaller than it is today. Periods when the sun passed through a denser interstellar cloud would have compressed the heliosphere inward. Periods when it passed through a void would have allowed the heliosphere to expand. Some researchers have speculated that these variations in heliospheric size might be connected to changes in cosmic ray flux at Earth, and through that, to changes in climate and biology. The cosmic ray climate connection is genuinely uncertain and contested among researchers, but the underlying physics that the heliosphere varies in size and that its size affects cosmic ray penetration is not contested. Voyager 1's measurements provide the observational foundation for understanding how large the heliosphere is right now, and for testing the models that predict how it has varied in the past. One of the things that stands out when you look back at the history of the Voyager mission is how consistently it has produced findings that nobody expected. Before the flybys of the 1970s, nobody had seen Eo's active volcanoes. The moon had been expected to be geologically dead, like Earth's moon cold, cratered, ancient. Voyager 1 revealed a world of continuous volcanic eruption, the most geologically active body in the solar system. That discovery came from a single image, analyzed by a scientist named Linda Morabito, who noticed a plume in the image while doing routine navigational calculations. It was not the kind of thing anyone had predicted. Before Voyager reached Saturn, nobody had seen the full complexity of that planet's rings. The rings were known to exist, but their fine structure, the thousands of individual ringlets, the gaps, the braided rings, the spoke features that appear and disappear was unknown. And the discovery of Titan's thick atmosphere of nitrogen, with organic chemistry already underway, changed thinking about where in the solar system the ingredients for life might exist. Before Voyager 1 crossed the heliopause, nobody had measured the temperature of the boundary zone. Nobody had measured the galactic cosmic ray flux unfiltered by the heliosphere. Nobody had found the persistent plasma hum. Nobody had expected the magnetic field to remain aligned across the boundary. Nobody had thought to look for cosmic ray shadows caused by solar pressure waves in the interstellar medium. At each stage of the mission, the actual data has been richer, stranger, and more interesting than the predictions. This is not because the people making predictions were uninformed. Many of the best scientists in the world have been working on these problems for decades. It is because the universe is more complicated than any model of it. And direct measurement consistently reveals things that indirect reasoning does not anticipate. The pattern offers a reason to expect that whatever data comes back from the remaining instruments in Voyager 1's final years will contain at least one more surprise. What that surprise will be is, by definition, unknown. But the track record suggests that something unexpected is still waiting in the data, in the behavior of the magnetic field, as it potentially rotates toward the undisturbed interstellar orientation, in the density measurements as Voyager moves into a new region of the local cloud, in the way the plasma around the spacecraft responds to whatever solar activity continues to drive waves outward through the medium. In September of 2027, Voyager 1 will mark 50 years since launch. Half a century of continuous flight. No other spacecraft in human history will have operated for that long by that date. None are expected to match it for decades after. And yet, in cosmic terms, 50 years of travel at 38,000 miles per hour is a barely measurable displacement. The probe has covered about 25.9 billion kilometers impressive by any human standard, but equal to roughly 0.00028 light years. The Milky Way is about 100,000 light years across. In 50 years, Voyager has covered roughly a billionth of the galaxy's diameter. This ratio captures something essential about the challenge of interstellar travel. The universe is not hostile to high-speed objects. There is no friction in deep space, no drag to slow Voyager down. The problem is simply that the distances involved are so vast that even the fastest object humanity has ever propelled through space barely registers against them. When people dream of interstellar travel, the obstacle is not engineering in the conventional sense. It is physics, the sheer distance, and the relationship between distance and time at the speeds achievable with anything like current or near-term propulsion. Voyager 1's 50-year journey puts this in stark, practical terms. To reach even the nearest star in a human lifetime would require speeds thousands of times higher than Voyager's. To reach it in a decade would require speeds tens of thousands of times higher. None of the propulsion concepts seriously studied for interstellar missions, nuclear pulse propulsion, laser-driven light sails, antimatter rockets, can plausibly achieve the speeds needed for anything faster than a centuries-long journey with current scientific and engineering knowledge. None of this diminishes what Voyager has done. It simply locates it accurately within the larger context. Voyager 1 is the farthest human-made object from Earth. It is the first human-made object in interstellar space. It has made discoveries that nobody anticipated, and that have shaped scientific understanding of the solar system's place in the galaxy. And it has done all of this while remaining fundamentally a piece of technology from the 1970s, running on 1970s software, driven by 1970s engineering, kept alive by the dedication of a small team of people who think the data it still produces is worth the effort. The most remarkable thing about Voyager 1 may simply be the persistence of it. The fact that a machine launched 49 years ago is still operational, still generating useful science, still providing unique data that no other instrument can replicate, that is not something the people who designed it were planning for. It happened because of physics. Yes, the near-perfect vacuum of space means the spacecraft has no friction to wear it down, no weather to corrode it, no gravity to pull it into a surface. But it also happened because of the quality of the engineering and the ongoing commitment of the people managing the mission. The RTGs are losing power. 2 instruments have been shut down in the last year alone. The memory chip that failed in 2023 will never work again. The backup thrusters that were dormant for 37 years before being tested in 2017 are one of the spacecraft's last fallbacks for attitude control. Every year, the list of things that could end the mission grows longer, and the list of things that might save it grows shorter. And yet, here it is, still talking, still measuring, still sending home numbers about the electron density and the magnetic field in a region of space that no human instrument had ever entered before Voyager 1 arrived. Every transmission that comes back from interstellar space is, in a narrow technical sense, a continuation of a mission that was supposed to end in 1982. Every scientific result from the last decade is a bonus, an unexpected gift from a machine that had already done more than anyone asked. That is worth noticing, not just as a human interest story about perseverance or engineering excellence, though it is both of those things, but as a reminder of what it actually looks like to do science well, to build something carefully, to maintain it patiently, to keep collecting data even when the results take years to fully understand, and to let the universe show you what it actually is rather than only confirming what you expected to find. Every signal from Voyager 1 is a time capsule. When a data packet arrives at the Deep Space Network dish in Canberra, it left the spacecraft more than 22 hours earlier. The electron density reading it contained, say, 0.14 electrons per cubic centimeter is a measurement of what the plasma around Voyager was like yesterday, not today. By the time scientists are reading that number, the spacecraft has already moved roughly 900,000 miles farther from the Sun. In a very direct physical sense, what we know about Voyager's current situation is always slightly out of date. The most recent measurement is always the most recent one to have had time to travel back. There is a built-in delay, a 22-hour news cycle, minimum between what Voyager is experiencing and what anyone on Earth can know about it. This is a consequence of the same speed of light limitation that makes operating the spacecraft challenging. It is also, in a philosophical sense, a feature of the situation rather than just a bug. Every observation of a distant object in the universe is a view into the past. When you look at the moon, you see it as it was 1.3 seconds ago. When you look at the sun, you see it 8 minutes in the past. When you look at the Andromeda galaxy, you see it as it was 2.5 million years ago. Distance is time in a universe where light moves at a finite speed. Voyager 1 is close enough that this effect is measured in hours rather than years. But it is the same underlying physics. What the spacecraft is experiencing right now cannot be known until a full day has passed. What it will encounter next week is unknowable until next week's signals arrive. The universe does not permit faster than light information transfer, and the 22-hour delay from Voyager 1 is a modest, concrete example of exactly why that constraint matters. When Voyager 1 finally goes silent, it will not be forgotten. The mission's data archive, everything recorded from 1977 through the end of operations, will remain accessible to researchers indefinitely. Papers drawing on that data will continue to be published for decades. The cosmic ray measurements, the plasma density time series, the magnetometer records, the temperature measurements at the heliopause, the isotopic composition data from beyond the boundary, all of it will continue to be analysed and reanalyzed as theoretical understanding improves and as new questions arise. Future missions, when they eventually launch, will be built partly on what Voyager found. A dedicated interstellar probe, if it is ever approved and funded, will carry instruments designed to answer specific questions raised by Voyager's data. It will cross the heliopause in a different direction with far better tools, and it will produce a richer and more complete picture of the interstellar medium than Voyager could provide. But it will be standing on the foundation that Voyager built. The students who are in graduate school today, learning heliophysics, studying plasma physics, working on models of cosmic ray transport, are the ones who will design that future mission. Some of them are already working with Voyager data as part of their research. The chain of scientific understanding that leads from Voyager's discoveries to whatever comes next is not broken by the spacecraft going silent. It continues in the notebooks and computers and conversations of the people who have been studying the data for years. And somewhere, roughly 50 billion miles from Earth, by the time that future mission launches, the original Voyager 1 will be continuing its journey, silent, unmonitored, carrying its golden record through the space between the stars, on its way to nowhere in particular, at 38,000 miles per hour, forever. Voyager 1 is not alone in interstellar space. Its twin, Voyager 2, crossed the heliopause in November 2018, 6 years after Voyager 1, in a different direction southward rather than northward, roughly toward the southern constellation Pavo. The two probes are now more than 4 billion miles apart from each other, each measuring the interstellar medium along its own trajectory. This is scientifically valuable in a way that a single probe cannot replicate. When Voyager 1 reports a particular magnetic field direction or a particular plasma density, there is always the question of whether that measurement reflects the general properties of the local interstellar medium or is specific to the particular path the probe is taking. When Voyager 2 makes an independent measurement from a different location and different direction, the comparison begins to answer that question. In broad terms, the two probes have found consistent conditions in the interstellar medium. Both detected the thermal boundary at the heliopause, the wall of heat produced by magnetic reconnection at the boundary zone. Both found the interstellar magnetic field to be unexpectedly parallel to the heliospheric field, confirming that this was not a coincidence or an artifact of the specific direction Voyager 1 crossed. Both found the galactic cosmic ray flux to be elevated compared to inner solar system levels. Both observed pressure waves from solar activity propagating into the interstellar medium, but there are differences too. Voyager 1 crossed the heliopause at 121 astronomical units. Voyager 2 crossed at 119. The two crossings happened during different phases of the solar cycle. Voyager 1 crossed during a period of lower solar activity. Voyager 2 during a more active period. The electron density profiles observed by the two probes show some differences in detail, consistent with spatial variation in the local interstellar medium and temporal variation due to the solar cycle. Voyager 2 has one instrument that Voyager 1 does not, a functioning plasma instrument. Voyager 1's plasma instrument failed shortly after the Saturn flyby in 1980 and could not provide direct plasma density measurements when the probe crossed the heliopause. Voyager 2's plasma instrument survived and gave the first real-time direct measurement of the plasma density jump at the heliopause crossing. The two probes are therefore scientifically complementary. Voyager 1's longer residence in interstellar space provides a longer baseline of data from beyond the boundary, while Voyager 2's intact plasma instrument provided better direct measurement of the crossing itself. As of 2026, Voyager 2 has 3 science instruments still operating, compared to Voyager 1's 2. The additional instrument on Voyager 2 is the plasma science instrument itself. When that probe eventually loses it to a power shutdown, direct measurement of the local interstellar plasma will depend entirely on the indirect technique that Voyager 1's plasma wave instrument uses. The two missions, taken together, constitute a stereo view of the very local interstellar medium. 2 data points, in 2 directions, from 2 instruments on 2 spacecraft that were built in the same facility, launched within weeks of each other, and have been flying for nearly 50 years. One of the most thought-provoking aspects of what Voyager 1 has found is how fundamentally it has changed the questions scientists ask about the solar system and its relationship with the broader galaxy. Before Voyager 1 crossed the heliopause, the standard picture of the heliosphere treated it largely as a feature of solar physics, something generated by the sun's output and shaped by the solar wind. The interstellar medium was a relatively passive backdrop, a uniform sea of thin gas through which the heliosphere moved. The properties of the heliosphere were driven from the inside by the sun, not by the outside. The Voyager data has substantially revised this picture. The interstellar medium is not a passive backdrop. It actively shapes the heliosphere, compresses it, and influences the cosmic ray environment inside it. The interstellar magnetic field, whose direction was measured for the first time at Voyager's location, affects the shape and boundaries of the heliosphere in ways that models are still working to fully capture. The temperature and density of the very local interstellar cloud determine how large the heliosphere is, with direct consequences for the long-term radiation environment at Earth. The discoveries about the wall of heat at the heliopause, the magnetic reconnection-driven temperature surge at the boundary revealed an energy conversion process at the edge of the solar system that nobody had predicted at the scale observed. The persistent plasma hum revealed a continuous low-level activity in the interstellar medium that previous measurement techniques could not detect. The cosmic ray anisotropy driven by solar pressure waves revealed a mechanism for the sun to influence the interstellar medium for unknown distances beyond its nominal boundary. Each of these findings was not just an answer to a question. It was the creation of new questions that did not previously exist in their current form. The wall of heat raised questions about the efficiency of magnetic reconnection at the heliopause boundary and about how that process varies around the boundary. The plasma hum raised questions about what drives persistent wave activity in the local interstellar medium and what physical mechanism is responsible. The cosmic ray anisotropy raised questions about how far solar influence extends into the interstellar medium and how long each disturbance persists before the medium relaxes back to its background state. Science works this way. Good measurements don't just confirm existing models, they generate new models, which generate new questions, which require new measurements. Voyager 1's data has been a prolific generator of new questions, which is exactly what good science looks like. There is a human dimension to this mission that tends to get crowded out by the numbers and the science, but that matters for understanding what has actually been accomplished. The people who built Voyager 1 knew that the planetary flybys would be the scientific highlight. They knew that after Saturn, the probe would continue outward into a region where there were no planets, no targets, nothing to visit. They could not have known in 1977 whether the spacecraft would survive long enough to tell us anything about that region. They could not have known whether the instruments would still be functioning, whether the RTGs would produce enough power, whether the computers would still be running. They built the spacecraft as well as they knew how, launched it, and hoped. What followed was a succession of engineering choices, made one at a time over nearly 50 years, that collectively kept the mission alive far longer than anyone planned for. Each time a thruster began to degrade, a backup was found. Each time a heater had to be sacrificed, the team found a way to keep the critical systems warm enough. Each time a memory chip failed, the team found a way to work around it. Each decision was made by people who understood that they were responsible for the last and only direct link to interstellar space. The scientists who have worked with the data over the last decade, the people who identified the persistent plasma hum, who puzzled over the magnetic field alignment, who tracked the anomalous elevation in field strength starting in 2020, have been doing science in a domain where there is only one data source, no way to repeat the measurement, and no possibility of sending a better instrument. They have extracted everything they could from what they had. That constraint make do with what exists, because nothing else exists is a feature of exploration at its most genuine. When the last signal from Voyager 1 finally stops arriving, the people who have spent careers on this mission will have been part of the only direct exploration of interstellar space in human history. Whatever comes after, whatever future missions eventually cross the heliopause with modern instruments, will have been built on the knowledge that Voyager generated. The mission that was supposed to last 5 years provided the foundation for a field of science that will continue for centuries. The signal from Voyager 1 arrives every day, a thin thread of data stretched across more than 15 billion miles of space. By the time it reaches the dishes of the Deep Space Network, it has been traveling for nearly a full day. Engineers assemble it into the packets, decode the instrument readings, and add another data point to the longest continuous record of the interstellar medium that humanity has ever assembled. The electron density around the spacecraft right now is approximately 0.14 electrons per cubic centimeter. The magnetic field is pointing in a direction that is slowly rotating, perhaps, as some models predict, toward the true orientation of the undisturbed interstellar field that lies beyond the heliosphere's influence. The hum from the plasma wave instrument is steady, giving a continuous read on the conditions of the medium through which Voyager moves. In a few months, Voyager 1 will be 1 light day from Earth. In a few years, its last instruments will likely go dark. In a few centuries, it will enter the Oort cloud. In tens of thousands of years, it will emerge from the other side and be, at last, truly between the stars in every sense beyond the sun's gravity, beyond its magnetic influence, beyond even the outermost boundary of the icy bodies it has gravitationally gathered around itself over billions of years. The golden record will still be attached, still carrying the music and the images and the greetings and the brain waves of a person thinking about love. Still carrying, encoded in the careful diagrams on its cover, a set of instructions for finding where it came from and how to understand what it contains. Whether anyone will ever find it is not something science can answer. Whether the effort to send it matters, whether it says something real about what humanity is and what we value, is not a question for instruments or data. It is the kind of question that a craft flying through the hum of interstellar gas, still talking after 50 years, somehow keeps raising whether you want it to or not. The hum goes on. The signal comes home. For now, that is enough. If you want to follow what comes next, the Big Bang maneuver, the 1 light day milestone this November, and whatever the interstellar medium still has to show us, subscribe so you don't miss it.